Hey everybody, welcome back. We're going to look at 7.4, which is proving trig identities. There is a section in grade 11 on the same thing, and I know from experience that a lot of people have difficulty with these identities, but they're like a puzzle. If you practice, you're going to become good at them, and the more you do, the more you'll enjoy them. So just buckle down, do your best, and we'll get through it. So first of all, what is an identity? Basically, a math identity is a statement that is true for all variables. So for example, if I gave you something like 3x plus 2x is equal to 5x, that's an identity. Because no matter what I choose for x, if I put it in for x on the left side, it will equal to the right side for all values of x in that expression. 3x is equal to 15 is not an identity because... got a spelling error there. It is only true when x is equal to 5. So that's not true when x is equal to 6, 7, 8, 9. So it's not an identity because it's not true for all variables. In grade 11, you went through certain identities, and these are the ones that we have listed here on our sheet. It says reciprocal identities. We know that cosecant, secant, and cotangent are the reciprocals of sine, cos, and tan, respectively. Our quotient identities. Well, that means tan is equal to sine divided by cos. And cotangent, well, if it's the reciprocal of tan, well, it should be the reciprocal of sine over cos, which is cos over sine. And the one that we have over here on the right was the most important one, probably in grade 11, the Pythagorean identity. We could use that a lot. Anytime we have sine squared x plus cos squared x was equal to 1. And you remember there were a lot of offshoots from that. So for example, if I brought cos to the other side, I know that something like sine squared x is equal to 1 minus cos squared x from that one. I can bring sine to the other side. You kind of get the same idea. Cos is equal to 1 minus sine squared x. And that just all derives from that original formula. And the two that we have below that are just the original Pythagorean formula when we divide everything by first one, cos squared x. That would give me this formula here, because sine divided by cos is the tan. Cos divided by cos, well, that's 1. And 1 divided by cos, secant. And finally, the last one that we have there is if everything in the Pythagorean identity was divided by sine squared x. So first, sine divided by sine is 1. Cos divided by sine is cotangent. 1 divided by sine is cosecant. So as long as I know the top one, that's really all that I need to memorize. You don't have to worry about remembering everything, because if we ever have something like this, one of our methods for solving identities was just change everything to sine and cos. So basically put it back into the original way that we're used to seeing it. So usually you don't have to memorize the bottom two. In grade 12, so recently we've learned about these identities here, or at least formulas here. We know the double angle formulas on the left side. We know cos had 3 different double angle formulas, depending on what we want. It's going to be useful here. And we had our addition subtraction formulas on the right side. Now, to prove identities basically means make the left and right side match without bringing numbers from the left side to the right side. Just work completely on the left side, then work completely on the right side, and we hope to see that the left and right side match. One of the important things for identities is being neat, so that somebody can follow your work. Instead of writing up in the top left-hand corner, then something down on the right side, and then on the back of the sheet and all over the place and say, left side equal right side, someone can't follow your work. So when we're proving something, we're proving it to somebody else. We got to show them that the left and right side match and be generally pretty neat. So the key to becoming a good identity solver is perseverance. So just not giving up. Keep practicing, you'll be okay. Some strategies that you can use are pick the most difficult side and work with that one. If you get stuck, put it back and start working on the other side. Try to write everything in sine and cos. That's probably the most important one, or the most useful tool. You can eliminate all the other ratios by just putting everything into sine and cos. If you see cosecant, put it into into sine. If you see secant, put it into cosine, for example. Also, if one side has a denominator, try to get the same denominator on the other side. or common denominators. Add them together. Try to get the same denominator on the same side to add two fractions. Try to recognize when we see double angles or compound angle formulas and compute those. Sometimes you may have to multiply by a conjugate. So what that means is if you have something like 1 plus sine x on the bottom of a fraction, right, or whatever's on top, you say, I don't know what to do. You can always multiply by the conjugate, which is 1 minus sine x. Basically the same values, just a different sign in between. And then use FOIL. And that's also one trick to simplify math. It's like when we were rationalizing some of those denominators for the exact values. All right, so let's get into it here. We want to make left and right side match. So first one here, prove that sine 2x over 1 plus cos 2x is equal to tan x. So a couple of things that we'll look for even before we start. I see a double angle formula on top, I see a double angle formula on the bottom, and I see a tan. I know that tan is equal to sine x over cos x. Okay, that's my right side. Right side here, left side's going to be on this side. That's as far as I can work on the right side. I can't do anything with those ones. Sine over cos is tan x. On the left side, I'm going to expand out those double angles. On top, we have sine 2x. So if you remember your double angles, that was equal to sine x, or 2 sine x cos x. Then from there, we have 1 plus double angle for cos. So I'm going to wait a second. What I'm going to do is I'm going to convert the double angle for cos, but I know that there's multiple ways that I can write that. So what I do is we look over on the other side and we say, well, I have cos on the bottom here. So I don't have a cos on the bottom on the left side. So I want to write the double angle formula that has cos. So if I go back up here, so double angle formula for cos, we have these three options. I think this one would probably be best because that has cos in it. And there's not sine for me to cancel out or anything like that. So I'm going to use the 2 cos squared x minus 1. And now we're going to simplify what we've got. So on the bottom, I guess on the left side, maybe I'll write the whole thing out. Whoops. Eliminate that bracket. I put that bracket because usually when we substitute something in, we put into a bracket. 1 plus 2 cos squared x minus 1. Remember, if this was minus, it would have to distribute to each of these terms. It's plus, so it stays the same. So look at what we've got here. I see on the bottom 1 minus 1. Well, that's going to be 0. Right? These will end up canceling out. So instead of rewriting the whole thing, I'll just cancel them right out. Now I look at what we've got here and see if we can cancel some things out. We don't have any addition or subtraction. They're just factors on the top and bottom, so I know that 2 can cancel out 2. I see a cos on the top and bottom. Up here, there's on the numerator, there's 1 cos. On the bottom, we have cos squared, so that means there's 2 of them. So if I cancel out the one on top, I'm only going to cancel out one of the 2 on the bottom. So that's going to work out to be sine x over cos x, which makes the left and the right side match now. And we're done. We proved that identity to be true on the left and right side. Keep going here. Second one. Prove that cos pi over 2 plus x is equal to minus sine x, or negative sine x. So you might look at this and say, well, I can't convert any of them to sine and cos because they already are sine and cos. Maybe on the left side, I see that I have a compound angle formula, the addition cosine formula. On the right side, I can't really do too much. That's just going to be negative sine x. Can't convert that, can't do anything with it. So what I'm going to do is I'm apply the compound addition formula for cos, which if you remember, it's cos of the first angle times cos of the second angle minus, it's the opposite sign, sine of the first angle, sine of the second angle. Now I can evaluate some of these because these two here do not have variables with them. Cos pi over 2. Well, cos pi over 2 is just 0. Sine pi over 2 is 1. So if I evaluate those, I get 0 times cos x. That's going to wipe that term out. On the right side, I have 1 times sine x. So 0 times cos x is just 0. I'm left with negative 1 or negative sine x. And we evaluate it. Left side now equals the right side. And we keep going. So they look like they're getting a little bit more confusing here. But I see cosecant 2x is equal to cosecant x divided by 2 cos x. So I'm going to write cosecant x over here, all over 2 cos x over here. And if I start working with this side here, I know that cosecant is just 1 over sine x. That's being divided by 2 cos x. And when you divide, it's like multiplying by the reciprocal. And when I multiply them through, I get 1 over 2 cos x. Actually, I'll put sine first. Usually we see it that way. Something like that. You might look at that and said, well, cosecant, I know it's on top, it's just the reciprocal. So when I put it on the bottom, it's sine, and that's all that happened. On the right side, I see a double angle formula for cosecant. We say, well, what the heck is that? Well, that's just the reciprocal of 1 over sine x. So if I evaluate the double angle for sine on the bottom, I'm going to have 1 over 2 sine x cos x. And what do you know? You look at the left side, look at the right side, and I see that they're the same now. Left side is equal to right side. All right, keep going here. Prove that cos x is equal to 1 over cos x minus sine x tan x. So the left side is just cos x. Can't do much with it. On the right side, we can work with that. We have 1 over cos x minus sine x. And I see tan. Instead of writing tan, I'm going to write sine x over cos x. So that's one of our tricks is anytime I see anything that's not sine or cos, make it into sine and cos. So on the right side, I'm going to rewrite this first fraction out here. When I multiply sine x times sine x, I get sine squared x all over cos x. Right? Multiply numerators and denominators like sine x over 1. Multiply them together. Now I have common denominators on the right side. That's good. I see 1 minus sine squared x all over cos x. Now we look at these ones and we say, okay, do I see any identities happening here? Maybe you say, yeah, on the top here, this is a Pythagorean identity for cos squared x. Remember? Because the Pythagorean was sine squared x plus cos squared x is equal to 1. So if I brought sine to the other side, 1 minus sine squared x. That's the same as the top. So the top is really cos squared x. And finally, to simplify this, you might say, well, there's 2 coses on the top, 1 on the bottom. So when I cancel them out, I lose 1. I'm left with just cos x. That's the same on the left side and the right side. We've proven that the left side is equal to the right side now. And one more to go. Prove that tan 2x minus 2 tan 2x sine squared x is equal to sine 2x. So that's a double angle formula for sine on the right side. So maybe I'll just write that out. That's about as much as we can do on the right side. On the left side is where our work is going to be done. So I'm going to rewrite the formula out, or at least the left side out here. Oops, minus. So you might say, I see double angle for tan, so I'm going to write that out as 2 tan x all over 1 minus tan squared x. And that's fine, you can work with that. However, you might find it a little bit easier, is I know that tan is sine 2x over cos 2x, right? That quotient identity. We said we find it a lot easier usually when we write in sine and cos, so just do that right away. You're going to find it makes your life much easier. You can solve it the other way as well. It's fine. So I have sine 2x all over cos 2x. Now the fraction we have over here, I'm going to multiply this whole part. So since they're whole numbers, just going to multiply by the numerator. And then I notice that we have the same denominator on the left and right side. So I'm going to push these ones together. While I do that, I'm going to evaluate these sine 2x's as well. I'm going to use the double angle formula for them. So the one on the left, I'm going to have 2 sine x cos x minus all the stuff that we have on the right. So I'm going to have 2 times 2 sine x cos x sine squared x. That entire thing over cos 2x. So now normally what we would do is distribute. So I'm going to distribute this negative inside. But what I'm going to do is I'm also going to simplify it a little bit because I know that 2 times 2 is going to be 4. So I'm going to make that 4 as well as I distribute my way through. So we have 2 sine x cos x, that's the left side, minus 4 sine x cos x sine squared x all over cos 2x. You can evaluate that one as well, but I'm going to leave it because I don't know what I want the cos 2x to be, whether I want it to be of the 3 formulas, whether the one with cos, sine, or both cos and sine, but we'll wait. So along the top, you might see that the right side of the top numerator has sine x and sine squared x. I can multiply them together for sine cubed x. So I'm going to write that as well. Simplify it a little bit. Make it a little bit easier. Oops. Like so. So now what I'm going to do is I can evaluate the top, but I still see 2 parts on top. What I'm going to do is common factor the top. So we have 2 sides, right? We have 1 here and 1 here. Let's see what they have in common. Well, they both have a common factor of 2. They both have a sine. They both have a cos. Let's see what we're left with. So if I take out 2 sine x cos x, I'm left with 1 for the left side. On the right side, we're going to have 2 sine squared x. So maybe you look at this and say, I see a couple formulas that may be familiar to me. I see the double angle formula here. So you can put it back in double angle form if you want. But the main thing is this one over here. If you know your double angle formulas, this in the bracket is the double angle for cos. That's why I didn't evaluate this one, because I wanted to see which form I would come up with. In this case, I came up with the sine one. So I'm going to cancel those out. It's gone. That leaves me with just 2 sine x cos x, which was what the right side was. So I'm going to all the way back up here. Remember the right side was just sine 2x. We evaluated it as 2 sine x. So we have LS is equal to our S. Left side equals the right side. We proved it. We did some factoring. We distributed inside, all that work to get that both are the same. So therefore, it's an identity left and right side match for all values of x. And that's that. If you have any questions.